Okay, this is part one of the introductory lecture on magnetism. Prior to watching this lecture, pause this lecture at this moment, and please take a look at the following 3 demonstration videos in the folder that I have prepared for you for today. First of all, magnetic forces. Then secondly, the shape of a dipole magnetic field associated with an ordinary bar magnet. And then also take a look at my compass needle demonstration as well, which illustrates that the Earth has a magnetic field. Go ahead and take a look at those 3 demonstration videos now. Okay, now that you've viewed those demonstration videos, let me take you through the basic qualitative aspects here of the magnetic force. Okay, first of all, as I noted in one of the demonstration videos, there are 2 sides or poles to each magnet. Okay, and then as you also saw in that opening demonstration video, there are 2 types of magnetic forces. There are forces of attraction and forces of repulsion. Like poles repel and opposite poles attract. Okay, as I noted, however, in that demonstration video, there are lots of similarities right off the bat between the electric force and the magnetic force. For example, like charges repel and opposite charges attract. You're sort of seeing the same thing here now with magnets, but in the context of the sides of a magnet, referred to once again as poles. So, as I do state in that demonstration video, because the 2 forces are similar to each other, that is the electric force and the magnetic force, are they the same thing? The answer to that question is no, because you saw an electrical charge has no effect on a magnet and vice versa. But because there are lots of similarities between the 2 forces, there are deep connections, it turns out, between the 2. We're going to see that then as we go forward here for the remainder of this unit on electricity and magnetism, as we now cover the magnetic force. Okay, now specifically we refer to poles of a magnet as poles for the following reason. Because of how they react when magnets, for example, are placed in the presence of the Earth's magnetic field. The Earth's magnetic field is shaped like a dipole. Okay, so for example, let's say that right here is the Earth like so, North Pole and South Pole geographically, and then right here is the Earth's equator. Okay, the Earth's dipole magnetic field is shaped in the following way. And as I draw these now magnetic field lines, I'm using the same rules here for drawing field lines as I did earlier when talking about the electric force and also the gravitational force. Okay, here's basically what you saw in my compass needle demonstration. The compass needle is just an ordinary iron bar magnet, and in this case it was placed in the presence of the Earth's magnetic field. Okay, because we're at one of the mid-latitudes here in Los Angeles, let's say that we have our bar magnet like so. Okay, now one side of the magnet points roughly in the direction of north, for example here in the room. That's why we refer to that side of the magnet as the magnet's north pole. And then the other side of the magnet points roughly towards the south here in this room. That's why we refer to that side of the magnet as the magnet's south pole. So this is why we refer to the sides of a magnet as the poles of the magnet, because of how basically it lines up here in the presence of the Earth's magnetic field. Okay, the magnetic field associated with the bar magnet itself looks almost exactly alike to that of the dipole magnetic field here associated with the Earth. So right here is the North Pole, here's the South Pole like so, and then a dipole magnetic field like you saw in one of my demonstration videos looks like this. Okay, once again using the same rules here for drawing the magnetic field lines as I did earlier. So a dipole magnetic field looks like this, associated with an iron bar magnet and also associated with the Earth. Why the Earth ends up having a dipole magnetic field, we'll look at that a little bit later on. Okay, now one major difference between the magnetic force and the electric force is as follows. With the electric force, you can isolate charge. In other words, you can have a positive charge all by itself. You can have a negative charge all by itself. That's not the case, however, with magnetism. If you take an ordinary bar magnet and you break it in half, you end up with two more magnets, each magnet with a north and a south pole. So imagine taking this bar magnet and breaking it in half like so. And when you do, you just end up with two magnets. Each one has a north pole, each one has a south pole. This is fundamental to nature. In nature, the way that we say this is that there is no such thing as long as we're aware of it, as much as we're aware of it, that is, there is no such thing as what is called a magnetic monopole. In other words, a magnetic pole that exists all by itself. In other words, there's a north pole all by itself or a south pole all by itself. As much as we know, as far as we've seen in nature, that does not occur. So there's no such thing, as we say, as a magnetic monopole. That's one major difference between the electric force and the magnetic force. Okay, at this point, go ahead and pause the video, and what I want you to do next is take a look at two more demonstration videos that I've posted for you in the folder. The magnetic force that's exerted upon a current carrying wire, and then secondly, the magnetic force that's exerted upon a moving electrical charge. Take a look at those two demonstration videos now. Okay, let me begin to describe to you what it was that you saw in those two demonstration videos and an expression that describes the force that's exerted upon the current carrying wire in the first of those two videos, and the force that's exerted upon the moving electrons and moving electrical charges in the second video. Before I do that, however, I do have to define one thing about the magnetic field, and that's the following: its direction. Okay, incidentally, by the way, we always refer to the magnetic field as B. Capital B refers to the magnitude of the magnetic field, and the units associated with the magnetic field's magnitude are referred to as the Tesla. Okay, exactly what is meant by 1 Tesla you'll see in one of my mathematical examples a little bit later on. At any rate, however, right over here we have a B field, as we sometimes say in shortcut. We have a B field here associated with a bar magnet, and then the direction of the B field is defined in the following way. Okay, the B field always points away from the North Pole, and then or alternatively towards the South Pole. Like so. By definition, this right here is the direction of the B field, and it goes from north to south. Okay? Okay, now that we kind of have that definition out of the way here, let me describe the basic mathematics of the two demonstration videos that we saw. Okay, so now this is the force exerted upon a current carrying wire when it is placed in the presence of a magnetic field. Okay, so here's what you saw in that demonstration. Okay, right here is the wire, and the conventional current I will say is flowing in this direction. The wire has a length associated with it. The length is referred to as L. Okay, now by definition, let's say that the B field, which was generated or created, by the way, by that neodymium magnet that I was using in the demonstration, let's say by definition that the B field points into the board like so. Okay, the symbol that we use to describe a vector that points into the board is a circle with a little X in it, like so. This is meant to represent the back end of an arrow that is pointing into the board like so. So then therefore the direction of the B field is like this. Okay, stated without proof, the ultimate mathematics behind magnetism is quite difficult to describe and analyze, but stated without proof, the magnitude of the force that you saw that is exerted upon the current carrying wire is the following expression. IL times B, where I is the current itself, L is the length of the wire, and B is the B field. There is a direction, however, associated with the force vector that you saw. We define the direction of the force vector by using what is called right-hand rule. Okay, right-hand rule is used in a number of different instances throughout physics and engineering. Specifically, however, for this case, right-hand rule behaves in the following way. What you do is you take the fingers of your right hand and you point your fingers in the direction of the conventional current I, which in this case is towards the top of the board. You then take the fingers in your right hand and you curl them in the direction of the B field, which points into the board like so. The direction of your thumb is then therefore the direction of the force vector, the magnitude of which is described by the following simple expression. So in that demonstration, you basically saw three vectors that were all perpendicular to each other. So I had my wire coming straight up, like down, like so. The current was pointing in this direction in the demonstration. Okay, the B field, when I manipulated my rare earth magnet, was pointing into the board. And then we saw, for example, in one of the demonstrations that I illustrated, a force of attraction. That is, the force vector that was exerted upon the wire was in this direction. And then what I did in that demonstration was I took my magnet and I reversed it. When I reversed it, I reversed the direction of the magnetic field. So instead of the magnetic field then pointing into the board, let's now say that it points out of the board. Okay, the symbol that we use to describe a vector that points out of the board is a circle with a little dot in it, like so. This is meant to represent the tip of an arrow that is pointing in this direction, perpendicular to the board, and that's the direction of the B field. Okay, the magnitude of the force that was exerted upon the current carrying wire is once again described by this expression here, but now we use right-hand rule to describe the direction of the force vector. In this case, what you do once again is you take the fingers of your right hand and you point them in the direction of the current, and then I curl the fingers in my right hand like so in the direction of the B field. Notice that's out of the board. The direction of my thumb is then therefore the direction of the force vector. In this case, in the opposite direction as before, like so. So this is why you saw a force of attraction in one portion of the video, and then when I flipped the magnet backwards, then you saw a force of repulsion. The magnitude of that force is described by the following expression. Now this expression here is basically describing the force that's exerted upon a current carrying wire due to a magnetic field. However, a little bit more fundamentally, what's actually happening here? What's actually happening here is that we have moving electrical charge that is in the presence of a magnetic field. When you do have moving electrical charge in the presence of a magnetic field, then a force is exerted upon that charge. A more fundamental way of describing this expression is the following. Okay, let's say that right here is a charge Q that is moving in this direction like so with a velocity vector V. Once again, let's say that a magnetic field is present. Let's say that that magnetic field then points into the board. So right here is the B field like so. Okay, the magnitude of the force that's exerted upon the moving electrical charge is equal to QV times B. It was essentially this expression here that you were seeing in the second of my demonstration videos. This was the magnetic force that was exerted upon a moving electrical charge when I brought my neodymium magnet close to the cathode ray tube. So if you haven't looked at that video, go ahead and pause this video here and take a look at that demonstration video in today's folder. What you were seeing in that demonstration is essentially this expression here. We once again describe the direction of the force vector by using right-hand rule. In this case, what you do is you take the fingers in your right hand and you point them in the direction of the velocity vector like so. You then take the fingers in your right hand and you curl them in the direction of the B field, which is into the board, and then therefore the force vector is upwards. Like so, on the diagram like this. So once again, those two demonstration videos, the magnetic force exerted upon a current carrying wire, the details of which are here on the top board, and then the magnetic force exerted upon a moving electrical charge, the details here on the bottom board. With respect to mathematical examples, we'll keep those examples as simple as possible. I'll do that in part 2 of today's magnetism lectures.